Okay, so today I'm going to talk about a very specific aspect of coal and coal ash that is a health concern, and that is the radioactivity of coal ash. So coals, just like rocks and soils, contain trace levels of radioactivity. We call this kind of background radiation that we are used to being exposed to. However, coals are also about 60 to 80, 90% carbon. And so when we combust coals for energy purposes, we are burning off that carbon. And when we burn off that carbon, that last 10 to 30% of the inorganics do not burn. And those inorganics are what kind of make up the fly ash or the coal ash. And the naturally occurring radioactive elements, the radioactivity is part of that part that didn't burn. And so that effectively gets concentrated in coal ash, which makes coal ash relatively much more radioactive than the coal itself, which is why we are concerned about the radioactivity of coal ash. About 40% of this coal ash that we produce every year is recycled in things like cement, but then about 60% of it is disposed into either dry landfills or wet ponds. And so that's where the concern comes in, that this radioactivity is potentially getting into the environment. As Jenny just talked about, we have evidence that these ponds are leaking in many cases, and so what does that mean for the radioactivity? Is the radioactivity getting into the environment? Those are some major questions that surround the radioactivity of coal ash. So when I'm talking about this radioactivity, I'm talking about mostly the elements uranium-238 and thorium-232. These are two radioactive elements with very, very long half-lives that have been around since the formation of the Earth. The thing about uranium and thorium, I say they don't come to the party alone. So when you have uranium and you have thorium, those are going to, with time, decay into a long string of other radioactive elements. With coal ash in particular, I'm going to focus on two radioactive elements, radium-226, which is part of that uranium decay chain, and radium-228, which is part of that thorium decay chain. And I focus on radium for a couple of reasons. The first selfish reason being that radium is very easy to measure in a laboratory setting. The second reason is that radium-226 and radium-228 have pretty relatively long half-lives compared to some of the other elements in these decay chains. And so radium-226 in particular has a 1,600-year half-life, which means if it gets into the environment, it's extremely persistent. It's going to take thousands and thousands of years for that to decay away. Radium is also relatively soluble, so if coal ash does get into the environment, there's the concern that radium will leach out into the water. And like I said, because it's very persistent, it can stay there for a long time. And then radium is a human health concern. Radium is very toxic. The next thing I want to mention is we can also almost get away with just looking at radium-228 and radium-226. And the reason for that is kind of relates to these principles of radioactivity that I want to go through really fast. So when you have a decay chain with uranium and thorium as these parents, they have these very, very long half-lives. The radioactivity coming from each of its daughters is going to reach this equilibrium point. And so the radioactivity that comes from each element in this decay chain is going to be a reflection of the original radioactivity of these parents. And so what we call this is secular equilibrium. This means that in the simplest case, you would have, if you have a rock or coal ash, perhaps you could have uranium, thorium, all these decay products, but they're also going to be at radioactivities that are equal to each other. So just knowing the radioactivity of radium-226 from one decay chain and radium-228 from the other decay chain reflects the total radioactivity from all of these elements. So we went out and we collected about 50 coal ash samples and about 10 coal samples. These samples came from power plants that at that time were burning coal from only one source basin. So many coal plants will burn blends of coal from different basins, but at the time of this sampling, we were trying to target plants that were only burning coal from one basin in particular. These basins are the major coal-producing basins in the United States, the Powder River Basin, the Illinois Basin, and then the Appalachian Basin. And the goal of collecting all of these samples was to characterize and quantify the amount of radioactivity associated with coal combustion residuals, or CCRs, in the United States. And then we wanted to take that a step further and investigate the processes that control these radioactivity levels in the CCRs. And finally, today we'll talk a little bit about what some of the implications, the human and environmental health implications of this radioactivity are. So to start, we're just going to talk about the total radioactivity coming from these coal ash samples. And when I talk about total radioactivity, I'm going to refer to it as the total radium activity. So that's that radium-228 plus radium-226. And like I said, in a way that is a reflection of the radioactivity coming from the uranium decay chain and the thorium decay chain. So that's why we look at both those combined. And we found that the total radium activity from coal ash is highest in coal ash coming from coals from the Illinois Basin. And this is then followed by the Appalachian Basin. And finally, coal ash associated with the Powder River Basin had the lowest total radium activity. We found that in general, across the board, the radioactivity in coal ash is about 7 to 10 times the radioactivity of the parent coal. And it's about 3 to 5 times the radioactivity of average values that we see for soils. This graph on the right shows radium-228 versus radium-226. And again, we look at the ratio of these two because it's a reflection of the ratio of thorium to uranium. And we found that coal ash from these different basins had distinct radium-228 to radium-226 fingerprints. And so the radium-226 to radium-226 ratio in the Illinois Basin was the lowest. In Illinois Basin, coal ash was the lowest at about 0.3. Powder River and Appalachian coal ashes had slightly higher ratios of about 0.7 up to about 0.1. And both of these trends, the total radioactivity and the radium-228, radium-226 ratios, what we saw in the coal ash was reflected in the coal. And so the highest radioactivity came from Illinois coals, with the lowest coming from Powder River Basin coals. And then the ratios we saw in these coal ashes were consistent with the ratios we saw from the feed coals. And this is to then illustrate what I was kind of talking about with that equilibrium. So if you didn't believe me, we went and we measured thorium and uranium in these coal ash samples. And so this graph on the left is radium-228 versus thorium, and the graph on the right is radium-226 versus uranium. And you see that these coal ash samples fall along that one-to-one line. And so the radioactivity coming from radium is a reflection of that radioactivity coming from thorium and uranium. Now this is kind of your easy scenario to imagine, and what we see then for nuclides from uranium through radium, thorium through radium. But that's not necessarily the case for every single element in that decay chain that we were looking at. So certain elements during the combustion process become volatile or more volatile than other elements because of the temperature at which they volatilize and the very, very hot conditions of the furnace. And so lead is one of those, and lead-210 is part of that uranium decay chain, one of the daughters of radium-226. And what we found was that lead-210 was actually much higher than radium-226 in fly ash samples. And the reason for that is you basically have, in a simple case, two types of coal ash. You have bottom ash, which is this heavy, wet, larger grained ash at the bottom of a furnace that's too heavy to rise. And then you have fly ash, which is a much finer grained, lighter ash that gets carried up into the stacks, and that's what's caught in those filters. So lead-210, because it's very, very volatile, will basically leave that bottom ash, go up with the flue gas, and then reattach itself to those finer grained fly ash particles. And that finer grained fly ash then has lead-210 from itself as well as what's come up from the bottom ash, so it's further enhanced in that lead-210. We also see this for polonium, although we didn't measure that, but other studies have measured polonium, which is one of the daughters of lead, and polonium is very, very toxic, and we see that polonium is also volatile and will also be further enhanced in fly ash. So this is a cool correlation that we found, and this gets at a lot of the drivers of the radioactivity that we see in coal ash. So what we set out to figure out was, what are the main things controlling the radioactivity in ash? Where are you going to get higher radioactivity ash? Where are you going to get lower radioactivity ash? What are the reasons for that? So we found two main reasons, and the first thing we looked at, or the first thing we saw, was that the uranium in coal, so the original amount of uranium in coal or the original amount of thorium in coal, correlated with how much radium you would get in the ash. So the more original uranium and thorium that was incorporated into the coal when it was formed, that's going to, the more you have of that, that's going to lead to higher radioactivity ash. And as we saw before, this varies basin by basin. So certain basins seem to have incorporated more uranium and thorium into the coal when they were formed, which is why we see differences between Illinois, Appalachian, and Powder River. The second driver of how much radioactivity you're going to get in your ash is the ash content of the coal. So we see two correlations here, one for high ash coal and one for low ash coal. High ash coal is going to contain up to about 40% ash, whereas low ash coal will contain up to maybe only about 10% ash. And so you actually get a much higher enrichment in low ash coal. Stopping working. In low ash coal, because you're burning off more carbon, you're getting, and so you're getting about a 10-fold concentration in radioactivity versus high ash coal, where maybe you're only getting a 3 to 4-fold enhancement. So what does this radioactivity mean in terms of human and environmental health implications? In a lot of ways, we aren't quite sure. So we know that coal ash affects water resources, but what we don't know really is, where's that radioactivity, what is the piece of that puzzle in terms of the radioactivity? And we have some ideas as to what the implications could be, but it definitely warrants further research. And so one of the concerns when we store coal ash in dry ponds and wet ponds is, can radium be leached out of those, and can that leached radium then reach groundwater or surface water resources? So radium is soluble under many conditions. Is that radium being transported elsewhere? Then the other concern is when we have spills. So these are pictures from the TVA spill and pictures from the Dan River spill. When you have coal ash being physically transported into water resources, can radium leach out under those circumstances, and can radium bioaccumulate then in the environment? The other concern is the inhalation of coal ash and then the inhalation of radioactive particles. And so if we store coal ash in dry ponds, as there's a movement towards, if those dry ponds are not properly lined, there's the concern for the resuspension of coal ash into the air, where it can be then breathed in. And when you're breathing in radioactivity, the major concern is breathing in alpha-emitting particles. So in those decay chains, certain elements emit different types of radiation, and one of those is called alpha radiation, which, if you inhale alpha-emitting particles, that is very damaging to your lungs. They're very large particles that will deliver a local dose of radiation to your lungs, and that's associated with lung cancer. One of these alpha-emitting particles is polonium-210, which we know to be further enhanced in coal ash. This graph down here just shows that you are going to increase your radiation in the air as you increase particulate matter, even if that is from dust, as dust has naturally occurring radioactive elements. But then if you add coal ash into the mix and you increase your proportion of coal ash that is making up that particulate matter, you're also going to further enhance how much radiation is in the air and people are exposed to. So that brings me to my conclusions, and we concluded from this study that in general, radioactivity levels in coals are about 7 to 10 times the radioactivity levels in the corresponding feed coal, and they're about 3 to 5 times the radioactivity levels in soils. Volatile elements such as lead and most likely polonium are even further elevated in fly ash, even above things like radium. And then elevated radioactivity, as well as those distinct radium-228 to radium-226 ratios can not only help us trace coal ash contamination, but give us something to think about for further studies whether this elevated radioactivity is getting into the environment and is causing human health concerns. So with that, I'd like to thank my funding sources and then the co-authors on this paper, as well as the Nicholas School of the Environment, and I thank you for your attention.
First of all, I enjoyed your presentation. Thank you very much. And one question I have is about the relevance of 3 to 5 times and 7 to 10 times of the soil levels. How relevant it is in terms of toxicity to human? Like I just Googled an EPA while I was listening. And the EPA website indicate that about 5 picocurie per liter kind of as a MCL levels. Mm-hmm. And I just wonder if you had a chance to, measure so that, what level we are dealing with over here.
Yeah, so the 5 picocuries that you see, that's the water limit. So there is a 5 picocurie per liter, which is 0.185 becquerels per liter limit for radium in water. And the levels we're looking at here is radium in that solid ash. And so a big question is, can that radium leach out of the ash, and can it leach out at concentrations that are high enough to go over that standard? And when I say that, I should also mention that while that's a standard, there is no, you ideally want your radioactivity to be as low as possible. So any amount of radium in your water is a concern. But in terms of whether radium is leaching out and affecting the water sources at levels higher than that standard, a lot is still very unknown and something that we are looking into working on, whether we see radium in outfalls, whether we see radium leaching from coal ash just in the lab. And so that's something that we are working on. And again, the concern then from just the solid ash itself, the concerns are a lot of times inhalation, and that is a little bit outside my realm in terms of that toxicity of inhaling that, but it incorporates how long you're exposed to it and how much you are breathing in. And ideally with radioactivity, you always just want to keep it as low as possible.
Thank you very much. I was curious if you mentioned exposure pathways in water and being worried about this leaching and in discharges to surface water, and then also the exposure to airborne dust particles. But I was curious if there's something about if you just have a massive pile of coal ash, if there's some other way that creates some danger of exposure, whether it's like, I don't know, excuse my extreme ignorance on this, but like fields of radiation or radon gas or something like that?
Right, so that's a good question. So I'm talking about whether you are physically taking in coal ash through inhalation or drinking the leachate. Radiation is dangerous in general in that it emits radioactive particles that can penetrate skin or if you're nearby. In terms of a large pile of coal ash, again, I'm not a toxicologist, and you always just hear you want to keep your exposure to radiation as low as possible. In terms of your exposure just being near a large pile of coal ash, well, I can't say if that necessarily will or will not lead to health effects. We are pretty used to background radiation, and we are exposed to different levels of radiation, whether we're in an airplane or where we are geographically and the rock type in that area. And so it all comes down to how long you're near it and how high it is. But where those thresholds are, I can't say for certain. And then what you brought up, radon is also an interesting point. So in those decay chains, radon is a gas, and we're concerned about radon a lot of times in our basements and places where it's closed in. And so a concern about radon, there's definitely a concern about radon with coal ash, especially with, I think, the workers who are working in those environments and maybe are exposed to those higher levels of radon. But that's something that other people definitely study, is how much radon is escaping that coal ash.